All right, buckle up, everybody, because today we're diving into something truly fascinating.
I love it when you say that. What have we got?
We're tackling a scientific paper that's generating serious buzz in the physics world.
Okay, lay it on me.
It's called the Universal Gravitational Theory.
Ooh, ambitious.
That's what I thought. And it's trying to answer some of those big questions about our universe, the kind that have baffled scientists for, well, like forever.
The really fundamental stuff, huh? I'm intrigued already.
Yeah, and the best part, you don't need to be a physicist to grasp the main ideas.
Music to my ears. I always said the universe should be accessible to everyone. So what's this theory all about? What's the core idea?
Well, they're proposing this concept of a gravitational medium.
A gravitational medium. That sounds like something straight out of science fiction.
It kind of does, doesn't it?
Yeah.
But it's actually a pretty elegant way to explain some of the things we've observed about gravity.
Okay, I'm all ears. Tell me more. What is this gravitational medium and how does it work?
So imagine it like an invisible fabric that permeates the entire universe.
Okay, I'm picturing it like a cosmic spider web.
Yeah, kind of. And this fabric, or medium, it interacts with matter and influences how gravity behaves.
So it's not just empty space out there, there's something more to it.
Exactly. And the really interesting part is that this medium, it's not uniform. Its density can change depending on where you are in the universe.
Okay, so picture a swimming pool.
Right,
Sometimes the water is calm and smooth, other times it's turbulent and choppy, yeah.
exactly. And this gravitational medium, it's like that. Its density fluctuates, and according to this theory, that affects how gravity acts in different parts of the universe.
Interesting. So are you saying that gravity might not be a constant force everywhere in the universe? That it could be stronger or weaker depending on the density of this gravitational medium?
That's exactly what they're suggesting. And they even use some pretty high-level math to model how it all works.
Okay, math. Not my forte. But is there any way we can explain this without getting too bogged down in equations? I mean, for the folks at home who, like me, are more into concepts than complex formulas.
Absolutely. They use this thing called a tensor field.
A tensor field?
It's represented by the symbol.
Hit me with it.
Yeah. And that tensor field basically describes how this gravitational medium interacts with all the stuff in the universe.
Okay, I think I'm following so far. But can we maybe ground this a little more? Relate it to something in our everyday experience?
Totally. Think about the difference between being in a crowded concert versus an empty park.
Okay, I like where this is going.
In that crowded concert, your movements are restricted, right? You're bumping into people, you're kind of stuck in place.
Yeah, it's all predictable, jostling and shuffling.
Yep.
Not much room for surprises.
Exactly. Now, that's kind of like gravity in a dense region of space, like our solar system.
Yeah.
Things are packed together, and gravity behaves the way we'd expect based on our classical understanding of physics.
Oh, I see. So the dense crowd is like a high-density gravitational environment.
You got it. Now think about that empty park.
Ah, much more freedom.
Right. You can move around freely, maybe do some cartwheels, who knows?
You know me so well. I do love a good cartwheel.
And that's kind of like what this theory suggests is happening in those less dense regions of space, like at the edges of galaxies. The gravitational medium is thinner there, so to speak, which could lead to some unexpected gravitational effects.
So the empty park is like the outer edges of a galaxy where the gravitational medium is less dense, and things can behave a little differently.
You nailed it. And that difference in behavior, well, it might just hold the key to solving one of the biggest mysteries in astrophysics. Dark matter.
Hold on, dark matter. That invisible stuff that supposedly makes up a huge chunk of the universe. Are you saying this theory can explain it away? I'm hooked.
That's what they're proposing. They're saying what we perceive as dark matter might not be invisible particles at all.
Mind blown. Okay, go on.
It could just be gravity acting differently in those low-density environments because of this gravitational medium.
So instead of a bunch of unseen matter holding galaxies together, it's just gravity behaving in a way we haven't fully understood before.
That's the gist of it. And get this, the paper even shows how this theory can reproduce the flat rotation curves of galaxies.
Flat rotation curves, you mean that observation that's usually attributed to, wait for it, dark matter.
The one and only. And that's just the tip of the iceberg.
There's more. This theory is really shaking things up. What else have they got?
Well, they also have a new take on dark energy.
Oh, wow.
You know, that mysterious force that's supposedly pushing the universe to expand at an ever-increasing rate.
Yeah, the one that's leaving cosmologists scratching their heads. So what are they saying about dark energy?
Instead of some separate unknown force, They're suggesting that this accelerated expansion might be driven by the gravitational medium itself.
Whoa. So they're basically saying, hey, maybe we don't need dark matter or dark energy if we understand gravity a little differently.
That's the core idea.
Okay, this is huge EE. If this theory is right, it's going to turn our whole understanding of gravity upside down.
It's definitely a radical departure from what we've always thought. But here's the thing.
Yeah.
Like any good scientific theory, this one needs to be tested.
Of course, how do they propose to do that? Can you actually see this gravitational medium or observe its effects directly?
That is the question. And that's where things get really interesting.
So how do we test this thing? Where's the proof?
Well, that's what makes this theory so exciting. It actually offers some pretty specific predictions that scientists can go out and try to observe.
Okay, I like it when a theory puts its money where its mouth is. Let's hear those predictions. What should scientists be looking for?
One of the big ones involves gravitational waves. You know, those ripples in space-time that are created when massive objects collide.
Yeah, the ones that LIGO and Virgo detect.
Those are the ones. Well, this theory predicts that those gravitational waves wouldn't travel at a constant speed through space.
Hold on, are you saying that the speed of gravity could change? That's like physics 101 stuff.
I know, right? It sounds crazy. But that's what this theory is proposing. It says that those waves would be affected by the density of the gravitational medium they're passing through.
Okay, so imagine those gravitational waves like a boat sailing across a lake. On a calm day, smooth sailing, full speed ahead. But if the water's choppy,
Yeah, the boat's going to slow down a bit, right?
exactly. And this theory actually predicts how much the speed of those gravitational waves should change depending on how dense the medium is in that particular region of space.
Which means that those super-sensitive detectors like LIGO and Virgo, they could actually look for these tiny variations in the speed of gravitational waves.
So we're talking about using our most advanced technology to potentially confirm a fundamental shift in our understanding of gravity. This is high-stakes stuff. What else does this theory predict?
Another big one has to do with that gravitational constant, G.
Ah, big G. The one that tells us how strong gravity is, right?
That's the one. And up until now, we've always assumed that G is constant, that it's the same everywhere in the universe.
Yeah, it's like a universal setting for how strong gravity is, right? Like a cosmic dial that's always set to the same number.
Precisely. But this new theory is suggesting that G might not be so constant after all.
Whoa, okay, you're really blowing my mind here. So are you saying that gravity might be a little bit stronger in some parts of the universe than in others?
That's exactly what they're saying.
Mhm.
And they think this variation in G would be tied to the density of that gravitational medium.
So denser medium, slightly stronger gravity. Less dense medium, slightly weaker gravity.
You got it. Now, those predicted variations in G, they're incredibly tiny.
But with precise enough measurements.
We might be able to detect them. And if we do, that would be huge GE evidence in favor of this theory.
Okay, so we've got these potential shifts in the speed of gravitational waves and maybe even a changing gravitational constant. Those are some seriously big implications. But what about on the grand scale, like cosmologically speaking? How does this theory change our understanding of the universe as a whole?
Well, think about the formation of the first galaxies. It's something that has puzzled scientists for a long time.
Right. The current models have trouble explaining how those early galaxies could have formed as quickly as they seem to have.
Exactly. It's like the timeline just doesn't quite add up with our traditional understanding of gravity.
So where does this gravitational medium fit into all of this?
Well, imagine it as sort of a cosmic scaffolding, something that permeates the entire universe and helps to guide matter together.
Ooh, I like that analogy. So instead of just relying on random chance for all that matter to clump together and form galaxies, this medium is kind of giving it a nudge in the right direction.
Exactly. It's like adding a new ingredient to the recipe for the early universe, something that could help explain how those first galaxies formed so quickly.
That's pretty amazing. And it makes you wonder, if this gravitational medium is really as fundamental as this theory suggests, could we ever learn to actually harness its properties? Like, could we use it for something?
Harness the fabric of gravity itself.
Yeah.
That's a pretty wild thought, isn't it?
It is. I mean, just imagine the possibilities. New forms of energy, maybe even revolutionary ways to travel through space.
It's like opening a door to a whole new realm of physics and engineering.
Exactly. But of course, we're getting ahead of ourselves. This is still just a theory.
Right. It's important to remember that this is all very theoretical and needs a lot more testing and scrutiny from the scientific community
Yeah.
before we can say for sure if it's the right way to understand the universe.
Of course, of course. But that's what makes science so exciting, right? This constant back and forth between bold ideas and rigorous testing.
Absolutely. And whether or not this specific theory turns out to be completely accurate, it's already sparked some incredibly important questions and pushed the boundaries of our knowledge about gravity and the universe.
Exactly. It's a beautiful example of how science moves forward. Sometimes it takes a radical new idea to shake things up and point us in a whole new direction.
Well said. And on that note, I think it's time to take a little break. But we'll be back in just a bit to wrap up this incredible deep dive and discuss what this theory might mean for the future of physics. And we're back. We've covered a lot of ground today, folks. This universal gravitational theory, it's really something else, isn't it?
It really is. And one of the things that strikes me is how this theory is presented. It's not like some grand declaration, this is how it is, end of story.
Right.
It feels more like an invitation to explore, to question, to test. There's a humility there that I find really refreshing.
I agree. It's like the author saying, hey, I think this might be onto something, but let's work together to figure it out.
Exactly. It's a true embodiment of the scientific spirit, open to collaboration, open to being challenged. That's how we make progress.
It really makes you appreciate the process of science, doesn't it? It's not about being right or wrong all the time. It's about constantly refining our understanding, getting closer and closer to the truth.
Couldn't have said it better myself.
Yeah.
And that's what makes this whole thing so exciting. We're watching science in action, seeing how these new ideas can spark debate and push us to think differently about the universe.
And who knows what amazing discoveries are waiting for us down the road as researchers around the world dig into this theory and put it through its paces.
It's like we've been handed this incredible map and we're just starting to explore all the uncharted territories it reveals.
And even if some parts of this theory end up needing to be tweaked or revised, the fact that it's generating this kind of excitement and pushing the boundaries of our knowledge, that's a huge EE.
Absolutely. It's a testament to the power of human curiosity, our drive to understand the universe around us.
It's funny, we started this deep dive talking about how you don't need a PhD to grasp the main ideas of this theory.
Because the universe belongs to everyone, right?
Exactly. But even with a basic understanding, it's mind-blowing to think about how this one idea could potentially revolutionize our entire picture of the cosmos.
It really is. We might be on the verge of a complete paradigm shift in our understanding of gravity and its role in shaping the universe.
And who knows, maybe this gravitational medium will turn out to be the key to unlocking some of the universe's biggest secrets, leading to breakthroughs we can't even imagine right now.
Now, wouldn't that be something? It gives me chills just thinking about it.
Well, on that note, I want to thank you for joining us on this incredible journey into the world of the universal gravitational theory.
The pleasure was all mine.
And to everyone listening out there, remember, never stop questioning, never stop exploring, and never stop being amazed by the wonders of our vast and mysterious universe. Until next time.